In 2022, this astonishing image was published. What makes it so astonishing? Well, this is one of the most detailed radio images of the center of our galaxy that's ever been produced. Assembled from the first survey using the full array at the MeerKAT Radio Observatory in South Africa, this image took 3 years of data analysis to complete. And it is revealing something thoroughly bizarre. Deep within the turbulent chaos at the center of the Milky Way are hundreds of highly ordered, one-dimensional filament-like structures, dangling inexplicably above and below the galactic center. These enigmatic filaments stretch for up to 150 light-years, yet are only 1 to 3 light-years across. The big question is, what are these strange, supersized strands? Now scientists are trying to unpick this MeerKAT image to work it out. I'm McColgan and you're watching Astrum. Join me today as we uncover the mysteries around one of the Milky Way's weirdest phenomena. We'll explore the happy accident that led to their discovery and the extreme characteristics that are leaving scientists baffled. The center of the Milky Way, 27,000 light-years from Earth, is a place of violence. This innermost region, the central molecular zone, spans 1,600 light-years and is, by all accounts, the most extreme part of our galaxy. Density, temperature, and turbulent velocity, a measure of chaotic fluid motion, are around 1 to 2 orders of magnitude higher here than anywhere else in the galaxy. The cosmic ray energy density, a proxy for energetic activity, is 2 to 3 orders of magnitude higher. This region is home to vast complexes of molecular gas, about 20 million solar masses worth, dense cosmic clouds, ionized plasmas, extreme cosmic ray energy, ultraviolet and X-ray radiation, and turbulent magnetic fields. It is a hotbed of cosmic activity, from the formation of stars to exploding supernovae. And let's not forget Sagittarius A star, the supermassive black hole 4 million times the mass of our Sun, at the very center of it all. These conditions are hugely exciting for astronomers, but they make the galactic center notoriously hard to image. Visible light can't penetrate the dense clouds of dust and gas. So researchers turn to other parts of the electromagnetic spectrum to lift the veil and reveal the secrets at the heart of the galaxy. Radio waves have the longest wavelengths of the electromagnetic spectrum, from a few millimeters to hundreds of kilometers, and the wavelengths in the range of millimeters to tens of meters are ideal for radio astronomy. They pass through the obscuring clouds of gas and dust, giving us a clear view of what lies beneath. In the early 1980s, Farhad Yusef-Zadeh, studying for his PhD, was using the Very Large Array Telescope in New Mexico to produce a radio map of a section of the galactic center. He was planning to study star-forming regions, but narrow strips of radio emission were streaking across the entire survey area, right through the parts he was interested in. He thought they must be artifacts in the data or imaging errors, which any scientist will tell you is highly annoying. So after much frustration and no luck resolving the problematic artifacts, he returned to the VLA to image again at another frequency. And that was when his eureka moment struck. At 4 a.m. one morning, he was comparing the two samples taken at different times using different wavelengths, and he saw the same structures in both images. This was no artifact. This was a very real finding, something unlike anything he, or anyone else for that matter, had come across before. Zadeh was seeing highly ordered structures where previously only chaos was thought to exist, and they had some very unusual features. Most striking was their vast scale. These were continuous, narrow strips of radio emission 50 to 100 light-years long, but only 1 to 3 light-years wide, dangling vertically above and below the central molecular zone, the most extreme part of the Milky Way. Some appeared in pairs or clusters running parallel to each other like strings on a harp, each separated by a standard distance of around 1 astronomical unit, the distance between Earth and the Sun. When he cross-checked them with the infrared data from that area, Zadeh also discovered they had no counterpart in that area of the spectrum. This told him they were non-thermal emissions, that is to say, they were not produced by heated gases. This was corroborated by other measurements such as spectral index and polarization, which showed that the filaments were highly magnetic and emitting synchrotron radiation. Synchrotron radiation occurs when electrons moving near the speed of light interact with a strong magnetic field, which begged the question, what on Earth, or should I say, not on Earth, was accelerating the electrons to such speeds? The emissions along the length of the structures were continuous, ruling out localized events like star formation or supernova remnants. So Zadeh dubbed them non-thermal filaments and suggested they were likely related to galactic scale phenomena. For a scientist, a discovery like this would have been like Christmas coming early. After all, what do you get a budding scientist and a space enthusiast? Galactic structures of unknown origin that no one had ever seen before. Or, if that doesn't fit into a box, a really nice watch, like the ones designed by Holzkern, the sponsor of today's video. Holzkern's jewelry and watches are all based around natural materials like wood, leaves, and stone. I love their high quality aesthetic, and the Whisperwood Coaleaf watch I've been wearing lately has looked and felt amazing on my wrist. Even my dad was impressed with Holzkern, and he's a jeweler by trade, so he knows what he's talking about, because Holzkern's items are made with natural elements. Each one is unique, and Holzkern doesn't make many to ensure responsible and ethical production. So if you're looking for the right gift for a loved one this Christmas period, see what Holzkern has on offer. They'll even pre-wrap it for you in a festive red or green box. Click the link in the description or the pinned comment below. If you buy before the 19th of December, you'll get it before Christmas Day, guaranteed, with free worldwide shipping. Products arriving in 3 to 5 business days. And custom fees to America covered. Just use my code Astrum at checkout for a whole 15% off your purchase for all products site-wide. Now, back to Zadeh. His observations didn't correspond to anything else in the known galaxy, and Zadeh had many more questions. Where did the non-thermal filaments come from? What was maintaining their linear structures over such vast distances of space and time? Why, when clustered, were they so evenly spaced? But almost as soon as this startling discovery was made, the trail started to go cold. The available telescopes at the time simply didn't have the sensitivity needed to provide answers. Over the next 35 years, only a handful of other vertical non-thermal filaments were revealed and categorized. Some were even given enigmatic names like the snake, pelican, and bent harp. Sadly, there wasn't enough data to make any great leaps forward in understanding. Well, not until 2022 and MeerKAT's mind-blowing image. The MeerKAT radio telescope at the South Africa Radio Astronomy Observatory, or SARAO, is comprised of 64 interlinked antennas, each with a 13.5 meter diameter parabolic dish spread over 8 kilometers of radio silent zone. Built over 4 years, the full array was inaugurated in 2018. Its location in the southern hemisphere is perfect for imaging the center of the Milky Way, thanks to our sun's axial tilt relative to its own position in the galaxy. So MeerKAT has a direct line of sight into the CMZ and the galactic center. Over the course of 3 years, An international team led by Dr. Ian Hayward and including Zadeh, now professor at Northwestern University, directed MeerKAT to a 6.5 square degree portion of the galaxy, a section of the sky around 30 full moons wide, with Sagittarius A star right in the middle. Using L-band radio frequencies of 856 to 1712 MHz, equivalent to wavelengths of 18 to 35 centimeters, they split this area into a 20-part mosaic, directing the telescope to survey each tile in turn over a total of 144 hours on target. This was the first time MeerKAT's full array was used, with 60 to 62 dishes sampling the sky at any one time. After generating 70 terabytes of raw data, the equivalent to 700 hours of 4K YouTube content, the team then had to process it. That was no mean feat. Given the complexity of the environment, they needed to put the data through a high-pass filter using a method called difference of Gaussians. This is a commonly used edge smoothing technique to remove background noise and enhance the visibility of fine structures, especially important for visualizing non-thermal filaments. And this is the result. More like a work of art than a scientific study, it captures a wealth of features. Some are well known, like Sagittarius A star seen in the central saturated area here, and clearer views of previously known supernova remnants and star-forming regions. This here is a supernova remnant. To its left is a runaway pulsar, the Mouse, and up on the right, one of the longest and most famous non-thermal filaments, the Snake. As noted by the team, one of the most startling discoveries was the sheer number of filaments apparent in the image, an order of magnitude greater than all previously known, most of which had never been seen before. This was game-changing for Zadeh and his colleagues. Now we finally see the big picture, a panoramic view filled with an abundance of filaments, he said. This is a watershed in furthering our understanding of these structures. There was finally enough data to carry out meaningful population studies. They set to work carrying out statistical analysis of the filaments. This work, published in the Astrophysical Journal Letters, not only further categorizes the filaments, but gives tantalizing clues to their origin. The new data confirmed that all of them are magnetized. In fact, the team found that the magnetic field was significantly greater, in some cases up to 10 to 100 times stronger than typical galactic magnetic fields. The new analysis also confirmed that synchrotron radiation is a defining characteristic. Interestingly, the MeerKAT data revealed that there is a steepening with galactic latitude. In other words, the filaments appear to cool as they stretch away from the galactic plane. This gives us a clue as to their possible origin. The electrons further away from the galactic plane could be older, implying that the filaments are related to past activity of Sagittarius A star. And there was another clue that suggested this too, enormous structures known as radio bubbles. First discovered by Hayward, Zadeh, and the MeerKAT team in 2019, these huge radio-emitting structures stretch symmetrically above and below the galactic plane, forming an hourglass shape thousands of light years across. They are thought to have been created by a phenomenal outburst from Sagittarius A star about 100,000 to a million years ago. An event powerful enough to leave such a scar on the galaxy could have been vast quantities of gas and dust falling into the black hole, or a huge and sudden burst in star formation close by. An incident like this would have triggered an intense outburst of energy and whipped up galactic winds, driving gas and cosmic rays violently away from the galactic center, stretching and amplifying magnetic field lines in its wake, creating those bubbles and non-thermal filaments. What's more, Strong magnetic fields, which as we now know are a confirmed characteristic of all filaments, capture cosmic rays. And the great thing is, we can date them. Those detected in the filaments by MeerKAT match the proposed period of the Sagittarius A-star outburst considered responsible for the radio bubbles. In other words, they are the same age. The position and capabilities of MeerKAT, alongside the same high-pass filtering used to resolve the non-thermal radio filaments, not only revealed these bubbles in astonishing detail, but showed almost all of the filaments are confined within them. This close physical association adds even more weight to the argument that the same energetic event created them. Something powerful enough to create the bubbles would certainly be able to accelerate electrons to near the speed of light, with the stretched magnetic field lines channeling them to produce the filament's signature synchrotron emission. With this hypothesis in mind, Zadeh and the team described the formation of non-thermal filaments as magnetized streamers in a cosmic ray-driven wind. It certainly paints a compelling picture for the possible origin of the filaments, but it is by no means conclusive, as even the authors themselves attest. Other theories are being worked on. With a mystery this tantalizing, other astronomers have been studying the filaments too, but this single image is still the one that's told us the most. Zadeh wasn't kidding when he said it was a watershed moment, but with so many unanswered questions, some going back 40 years, where does that leave us? Are non-thermal radio filaments merely a galactic curiosity? Not by any means. They are a riddle wrapped in a mystery inside an enigma, and could shed light on one of the biggest unanswered questions out there: how supermassive black holes regulate star formation within a galaxy. Scientists know that the active centers of galaxies must transfer energy and matter into interstellar space through a process called galactic feedback. If they didn't, star formation would run away unchecked, using up a galaxy's gas and dust faster than observations tell us. But how this feedback happens is unknown. MeerKAT's detailed imagery of non-thermal filaments and the radio bubbles provides us with compelling evidence that this outflow of energy could happen in discrete but powerful outbursts. And this is something that has been seen before. Fermi bubbles, discovered by NASA's Fermi Gamma Ray Telescope in 2010, are even bigger, hourglass-shaped configurations spanning a total of 50,000 light-years. These mind-bogglingly massive structures, colored magenta in this image, are thought to be millions of years old, likely caused by a violent outburst from Sagittarius A-star, which calculations suggest had the energy of 100,000 supernovae. This is much more powerful and ancient than the event proposed to have made the filaments and radio bubbles, but together they paint a picture of intermittent outbursts from deep within the heart of our galaxy. Both have the potential to regulate star formation, ensuring that the Milky Way doesn't suffer from burnout. As scientists continue to unravel the mysteries of non-thermal filaments and tackle the big questions about how the universe works, the trail doesn't seem to be going cold again anytime soon. Since the first full-array image, MeerKAT has found more of these mystery strands in other galaxies, with very similar properties to the ones we see in the Milky Way. Their very existence elsewhere suggests a common, underlying mechanism that alludes to their role in fundamental galactic processes. To conclusively piece together the whole picture will require another step change in imaging resolution. And hopefully that's not too far off, as MeerKAT, already awarded by the Royal Astronomical Society for its spectacular observations in radio astronomy, was built with longer-term goals in mind, namely to be incorporated into the square kilometer array. With a total collecting area of 1 square kilometer, it will be 50 times more sensitive than any other radio instrument in existence, and it's expected to be fully constructed by 2028. Keeping an eye on developments in other parts of the electromagnetic spectrum will be important too. Zadeh believes that the next breakthrough will come from gamma ray telescopes. Imaging at higher frequencies results in higher resolution imagery, which has potential to show us whether the filaments the radio bubbles that contain them, and the vast Fermi bubbles are connected. There's an elegance in order rising out of chaos, and observing non-thermal filaments streaming out through the cosmic winds certainly fits that notion. So keep watching this space, and with images and phenomena this spectacular, I certainly have no problem doing that. I'm happy to announce we have a weekly newsletter to keep up with all the discoveries in our cosmos, and our designer Peter has made the most beautiful email you'll ever receive. Sign up with the link down below. It's the best way to stay connected between videos. Short, focused updates on what's new and fascinating in space each week. No spam, no filler, just the good stuff. You'll get the latest news, visuals, and insights delivered straight into your inbox. If you enjoy Astrum videos, you'll love this. Join the newsletter and stay curious with us.